All right, let's hope that everything is working properly. It seems like maybe the audio wasn't on for the first few moments, but again, here's the script of the problems that we will be doing today. This is the order in which I'll be doing them, so if at any point in this video you wish to skip ahead, certainly feel free to do so. Then what I'll be doing is I'll be making PDF files out of all these pages, so if you simply want to look at some of the pages with things worked out and you want to go through at your own pace, feel free to do so. So let us begin. So first problem, Mr. Nimble Fingers over here. First problem, this will be page 1 for us. So this is section 2.4, number 39. And again, I'll be checking these off as I do them. So 2.4, number 39. Take me a while to find the page. All right, 2.4, number 39. In this problem, we want to determine if the S is closed on the operation. In this set S are the polynomials of degree less than or equal to 1, where the operation is ordinary addition. Well, let's just play for a moment before I actually get down to the solution. If we're going to play, if you think about it, if you take a polynomial, there's a polynomial of degree less than or equal to 1 with real coefficients. Here's another polynomial of degree less than or equal to 1 with real coefficients. And if we add them, the constant terms get added. The x terms get added. You can factor out the pi minus 8. And notice, if these were real numbers, so are these, because the real numbers are closed under addition. If these are real numbers, so is this, because the real numbers are closed under addition. Let's see, let me just spend one moment looking at what it says on the bottom of the screen there. Okay, no problem. So again, if you look at this more generally, I don't think there really is a need to look at this more generally. The way you add two polynomials with real coefficients are, you add the constant terms, you add the x terms. Notice, if these both started off as degree less than or equal to 1, this will also end up being degree less than or equal to 1. So this one is indeed closed. Let me just knock that off our checklist here. Next one is number 40. For number 40, we're looking at the same exact set, except in this case, 0 is, or circle, is multiplication. Well, again, let's just sort of play. Suppose we took 1 plus x times 1 minus x. Again, this is just one example. But when we multiply, we get 1 minus x squared. Well, what this indicates to us is if we take something of degree 1 and we multiply by something of degree 1, we're going to get something of degree 2, which isn't in S, because everything in S has degree less than or equal to 1. So here's an element in S, degree 1. Here's an element in S of degree 1. The product has degree 2, so it's not an S. So in this particular case, the set at S is not closed. So that takes care of number 40. Let us move to the next requested problem was number 50. Number 50 says, let S be the set of polynomials with integer coefficients. So S is our good friend, the set of polynomials with integer coefficients, and circle is ordinary multiplication. Well, if you think about it, and again, maybe I'll be more general and it's really necessary. You start with a polynomial where all the coefficients are integers. You take another polynomial where all the coefficients are integers. And how do you multiply? Well, you do a lot of associative law, a lot of distributive law, and so on. But notice, again, if you're getting the constant term, you're just multiplying two integers. If you're getting the degree x, if you're getting the degree 1 term, you multiply these two integers, you multiply these two integers, and then you add. That gives you the coefficient of x. In other words, what's going on here is whether you're finding the constant term, the degree 1 term, the degree 2 term, the degree 3 term, all you're doing is you're multiplying and adding integers. Well, since the set of integers is closed under both addition and multiplication, if you start with polynomials with integer coefficients, you end up with polynomials with integer coefficients. So in this set, once again, the set is closed. Now let's move to 2.4, number 50. Sorry, just did that. Absent-minded professor. 2.4, number 53. Let S be the set of polynomials with rational coefficients of degree less than 50. So S equals the elements of QX of degree, and we are told less than 50. And circle here is ordinary multiplication. Well, as we know, if we're dealing with polynomials with rational coefficients, which one does all the time in Algebra 1 and Algebra 2, the degrees add. So if you take degree 3, which is in here, times degree 8, which is in here, you get degree 11, which is in here. Or if you take a degree 20, which is in here, times a degree 21, which is in here, you get a degree 41, which is in here. But notice, since degrees add, you can certainly start with two polynomials whose degree is less than 50 and get something whose degree is not less than 50. So for example, if you took x to the 49th, degree less than 50, x squared, degree less than 50, the answer is x to the 51, degree not less than 50. So this polynomial is in the set S. This polynomial is in the set S, but the product is not in the set S. So in this particular set, in this particular case rather, the set S is not closed under multiplication. And that takes care of the problems from section 2.4. Now let's move to the section of the problems after section 4.3. Again, it'll take me a few moments to actually find them. Here we go. Excellent. Okay, so moving on to page 3 here of today's notes. What we're going to be doing here is 4.3, number 18. So 4.3, number 18 says, tilde will be defined on R of x, the set of polynomials with their coefficients. We'll need to determine which of the reflexive, symmetric, and transitive properties are satisfied. if a property fails, provide an example that illustrates its failure. So for 18, we're going to say that two polynomials are related if and only if the value of f at c is less than the value of g at c for some c in R. And this word sum is very important. In other words, all it means is there only has to be one point where f is less than or equal to g. F could be bigger than g almost all the time, but there only has to be one point where f is less than or equal to g in order for these to be related. In other words, again, for almost every real number, f could conceivably be bigger than g. You just need one point where f is less than or equal to g. So when we check reflexive, the question is f of x related to f of x? That's the question. Well, that means f of c is less than or equal to f of c for some real number. Well, as you can see, no matter what number you plug in here, you get the same answer. So when you plug in 5, these are the same. When you plug in 15, f of 15 is the same as f of 15. When you plug in -8, f of -8 is the same as f of -8. In other words, not only is f of c less than or equal to f of c for some real number, f of c is less than or equal to f of c for all real numbers. And that's not necessary. You just needed some. So the point is reflexive holds. What about symmetry? Well, what we probably should be used to is if you've got something like a less than or equal, and you go for symmetry and you flip them, if one direction is true, the other direction is false. So probably the easiest examples, probably if they work, are constant polynomials. Suppose f of x is the polynomial that's always equal to 1, and g of x is the polynomial which is always equal to 2. So it turns out that not only is f of c less than or equal to g of c for some real number, but f of c is less than or equal to g of c for every real number, because no matter what real number you plug in, this side gives you 1 and this side gives you 2. So in this case, f is related to g. But if we want to check, is there some c that makes this true, no matter what real number you pick, g gives you a value of 2, and 1 gives you a value of 4. So for this particular example, f is related to g, but g is not related to f. Now, there are going to be lots of examples if you take non-constant polynomials where f is related to g and g is related to f. But to show that something is not symmetric, you only need one example where f is related to g, and when you flip the order, you get a different answer. So this one is not symmetric. Excuse me. Now comes the tricky one, transitivity. So suppose f is related to g and g is related to h, must f be related to h? Now this is sort of tricky because of the word sum. In other words, there might be some point where f is smaller than g. There might be some point where g is smaller than h. If these were the same points, like suppose f of 5 was less than or equal to g of 5, and suppose g of 5 was less than or equal to h of 5, then f of 5 would be less than or equal to h of 5. But the for some means there's some number that makes f smaller than g, maybe it's 5. There's some number that makes g smaller than h, maybe it's 10. But is there some number that makes f smaller than h? Well, not necessarily. And all this talk, I think, makes things kind of unclear, but I think a picture will make things quite clear. So let me draw this one. So suppose f of x is always equal to 2. And suppose h of x is always equal to 1. So no matter what real number you pick, whether you pick 5, whether you pick minus 5, whether you pick 0, f is always bigger than h. So no matter what real number you pick, f is greater than h. In other words, f is not related to h. So what? Well, suppose g is just the straight line g of x equals x. So if I compare g to f, sometimes f is bigger, like over here, f is bigger than g. Sometimes g is bigger, like over here. But the point is there a point where g is bigger than f? Sure, at 3. Sorry, I should write g of x is equal to x. At 3, g gives you 3, f gives you 2. So f of 3 less than or equal to g of 3. So in other words, f is related to g. Well, same sort of reasoning. There's this whole region over here where g is smaller than h. And there's this whole region over here where h is smaller than g. So in particular, if I want to know if g is related to h, is there a point where g is less than or equal to h? Sure, how about at 0? G of 0 is 0, h of 0 is 1. So there's a point where g is less than or equal to h. So again, to see that f is related to g, at the point 3, g is bigger. G is related to h because at 0, h is bigger. But different points work here, and there's no point that ever makes h bigger than g. So notice f is related to g is related to h, f is not related to h. This was a tricky one. It really required, among other things, it probably requires me letting you be able to, let me see if I can get that off the screen. There we go. Okay. So, again, this really required you understanding the purpose of quantifiers or what quantifiers mean. So again, f is related to g is related to h, but f is not related to h. So this one is not transitive. So that takes care of 4.3, number 18. Again, kind of tricky because it definitely required really understanding what quantifiers mean. Next one, again, everything from now on will be from 4.3. 4.3, number 21. Number 21. Same set of polynomials, but now we're going to say that f is related to g if and only if, let's see what the condition is in 21, if and only if f of c minus g of c is a rational number for every real number. Rather, f of c minus g of c, I don't know if I said that right the first time, f of c minus g of c is a rational number for all real numbers. So let's check. reflexive? Is f of x related to f of x? I wrote g, I meant f. Is f of x related to f of x? This means is f of c minus g of c. I've heard of minding your p's and q's. I'm having trouble minding my f's and g's. Is f of c minus g of c a rational number for all real numbers? And the answer is no matter what real number you pick, f of c minus f of c, since this is the same number, no matter what real number you pick, f of c minus f of c is in fact 0, which is a rational number. So this is reflexive. Okay. What about symmetric? So let's suppose f of c minus g of c is rational for all real numbers. Again, not saying that you always get the same rational number here, but no matter what real number you plug in, you get a rational number here. The question is g of c minus f of c rational for all real numbers? Well, the point is, if you pick any real number and you compare f of c minus g of c and g of c minus f of c, they're negatives of each other. So if f is related to g, no matter what real number you pick, this is rational, which means this is also rational because these are just negatives of each other. So no matter what real number you pick, this is going to be the negative of a rational number, which is also rational. So this one turns out to be symmetric. The final one is transitive. So let's suppose f of c minus g of c is rational for all real numbers, as opposed to like the previous problem, not some, but all. So this means f is related to g. Let's suppose g of c minus h of c is rational for all real numbers. Again, that means g, or this is what it means for g to be related to h. So now the question is, for every real number, let's say for every real number d, is f of d minus h of d a rational number? So there's the question. For every real number d that I plug in, is f of d minus h of d a rational number? Well, here's the point. F of d minus h of d is the sum of f of d minus g of d and g of d minus h of d. Well, notice the value f minus g is rational for every single real number. So that's rational. Notice the value at g minus the value of g minus the value of h is rational for every single real number. So no matter what real number you pick, this is rational and this is rational. So the sum is rational. So this is indeed a rational number. So if f is related to g and g is related to h, yes, indeed, f is related to h. So this is indeed transitive. And the key is the quantifier for all. It's not for some, but it's for all. And you can see in this case, this makes an enormous difference. That takes care of number 21. And then our notes, that'll get us to page 5. So coming after 21 is 4.3, number 22. again, 22 same set, but we're going to say that F is related to G if and only if it's no longer f of c minus g of c is rational for all, but just for some. So f of c minus g of c is rational for some real number. So you only have to find one real number that does the trick. So let's take a look. In terms of reflexive, f of x is related to f of x if and only if f of c minus f of c is rational for some real number. Well, it turns out not only is f of c minus f of c rational for some real numbers, but every real number you pick, f of c minus f of c is rational. Because no matter what c you plug in, since you're plugging the same c into f both times, f of c minus f of c is 0. So this one is reflexive. What about symmetric? Well, so suppose f of x is related to g of x. That means there exists some real number such that f of c minus g of c is rational. So it might be that f of c minus g of c is rarely rational, but at least there's some point where f of c minus g of c is rational. Well, notice for this particular number, g of c minus f of c is the negative of f of c minus g of c. And since this number is rational, the negation of a rational number is also a rational number. So if you can find some point that makes f minus g rational, that same point makes g minus f rational. So if f is related to g, that tells us that g is related to f. So indeed, this is symmetric. Now we come to transitive. Well, same problem as we had a few times ago. Let's suppose f is related to g and g is related to h. So this means there exists some point c1 that makes f of c1 minus g of c1 a rational number. And there's a point here that makes this difference rational, but it might be a different point. So this is c2 such that g of c2 minus h of c2 is rational. And we want to know, does there exist a point such that f of c3 minus g of c3 is rational? Well, so again, there's some point that makes this difference rational. There's some point that makes this difference rational, but these points could be different. If these points were the same, you could add and you'd be done, and the answer would be rational. But what if these points are different? And let me, again, kind of draw a picture like before. Suppose h of x is pi, and f of x is 1, and g of x is x. And let's study this picture. Notice there's a point where f and g are the same, namely at 1. So at 1, f of 1 minus g of 1 is 0. So there is a point, namely 1, that makes f minus g rational, so f is indeed related to g. If we follow the graph a little bit further, up here at pi, g of pi and h of pi are both equal to pi. So for an entirely different number, namely 1, h and g give you the same value. So g of pi minus h of pi is rational, or 0. So g is related to h. Now the question is there a point that you can plug in such that the value of f minus, this should be an h, that the value of f minus the value of h is rational? But notice, no matter what real number you plug in, f gives you 1. No matter what real number you plug in, h gives you pi. So, I think I feel a sneeze coming. Is it coming? There we go. Okay, so notice there is a real number that makes f and g the same. So you get 0, which is rational. There is a real number that makes g and h the same. So the difference is 0. But no matter what real number you pick, since f and h are constants, no matter what real number you pick, the value of f minus the value of h is 1 minus pi, which is not rational. In other words, f is not related to h. So f is related to g, g is related to h, f is not related to h. So in other words, this one is not transitive. And again, dealing with all these quantifiers can get fairly tricky. That takes care of 22. Let's move to 23. Again, same set. But now the question is, we're going to look at f of x is related to g of x if and only if the value of f minus the value of g is an integer for all real numbers. Well, maybe I'll go through this kind of quickly because it's kind of similar to a bunch of things we've done before. Again, in terms of symmetric, is f of c minus f of c an integer no matter what you plug in? Well, no matter what you plug in, f of c minus f of c is 0. So this is symmetric. In terms of reflexive, suppose f of c minus g of c is an integer for every real number. That means g of c minus f of c is just the negative of an integer. So f is related to g implies g is related to f because, again, no matter what real number you plug in here, you get an integer. That means no matter what real number you plug in here, you get the negative of an integer, which is also an integer. So this one is reflexive. And now comes our good friend transitive, where everything sort of depends upon this for all versus for some. So suppose, and hopefully you're getting pretty good at this point, f is related to g and g is related to h. So this means f of c minus g of c is an integer for all real numbers, not just some. And g of c minus h of c is an integer for all real numbers, not just some of them. So the question is f of c minus h of c an integer for all real numbers. And now we'll see how essential that for all is. F of c minus h of c is the sum f of c minus g of c plus g of c minus h of c. Well, this isn't an integer just for some real numbers. This is an integer for all real numbers. So no matter what real number you pick, this is an integer. Similarly, no matter what real number you pick, this is an integer, meaning this is the sum of two integers, which is also an integer, meaning f is indeed related to h. So this does indeed turn out to be transitive. Again, it's the huge, huge difference between for all and for some. Okay, that takes care of 23. Let's move to 4.3, number 25. As we move to page 7 of our notes. Okay, so 25, multi-parter. For the set Z, define tilde as A is related to B if and only if A minus B is divisible by 5. Well, I'll go through some of these kind of quickly, and then I'll get to the ones that I think were the hard parts for you. For A, show this as an equivalence relation on the integers. So for reflexive, the question is, no matter what integer you take, is A minus A divisible by 5? And again, A minus A is equal to 0, which is divisible by 5. So yes, reflexive. What about symmetric? So suppose A is related to B, is B related to A? So in other words, you know A minus B is divisible by 5. Question, is B minus A divisible by 5? Well, the point is these are just negatives of each other. So if A is related to B, this difference is divisible by 5, but this is just the negative of something divisible by 5, so it's still divisible by 5. So if A is related to B, B is indeed related to A. They're symmetric. And for transitive, suppose you're given A is related to B and B is related to C. Is A related to C? Well, remember, A minus C is A minus B plus B minus C. If A is related to B, this is a multiple of 5. If B is related to C, this is a multiple of 5. If you add together two multiples of 5, you get a multiple of 5. So if A is related to B and B is related to C, then A is indeed related to C, and there's your transitivity. Let's move on to the later parts of the problem. Part B, how many equivalence classes are there? Well, if you think about it, if you divide by 5, your possible remainders are 0, 1, 2, 3, and 4. Well, so in particular, just for the moment, look at the numbers 0, 1, 2, 3, 4. For any of these things, they're not related to each other. Because if you take the difference of any two different one of these, it's not going to be divisible by 5. Like 2 minus 0, not divisible by 5. 4 minus 1, not divisible by 5. So there are at least 5 classes, but notice if you took any integer and divide by 5, you get a quotient and a remainder, and the remainder is either going to be 0, 1, 2, 3, or 4. Well, if the remainder is 0, it's in this class. If the remainder is 1, it's in this class. If the remainder is 2, it's in this class. If the remainder is 3, it's in this class. And if the remainder is 4, it's in this class. In other words, there are only 5 equivalence classes. And the easiest names that we can probably give them are the class containing 0, the class containing 1, the class containing 2, the class containing 3, and the class containing 4. So there are 5 equivalence classes. How many elements are in each class? Well, notice if you took 0, every time you keep adding 5, or every time you subtract 5, you get a different element of the class. In fact, for any one of these numbers, every time you add on a copy of 5 or subtract a copy of 5, you get a new element of the class, meaning each class has an infinite number of elements. So there are 5 classes. Each class has an infinite number of elements. Next, list 5 elements in the class of 23. Well, if you want 5 elements in the class of 23, all you have to do is, well, 23 is in there, but you could start adding on copies of 5. 28's in there, 33's in there, or you could start subtracting copies of 5. 18 is in there, 13 is in there, because again, anytime you add or subtract copies of 5, you stay inside this set. Now, list 5 elements in the equivalence class of 19, or, sorry, minus 19. I shouldn't say equals, but these are contained in here. For minus 19, well, minus 19 is in here. But again, every time you add 5, like to get minus 14 or to get minus 9, or subtract 5 to get minus 24, to get minus 29, every time you add or subtract 5, you get a new element of the set. So again, this set has an infinite number of elements, so there are lots of answers. This set has an infinite number of elements, so there are lots of answers. But the way that you get answers are you add or subtract copies of 5. So that takes care of number . Well, hopefully there was not a break in the recording there. But again, as the saying goes, who knows? Well, let's hope we're back to the meeting here. If not, we'll see what we can do. Okay, this is 4.3. Number 29. So 4.3, number 29. Polynomials with real coefficients, and then we're going to say that they're equivalent if and only if they have the same derivative, which, if you think about it, and hopefully this is familiar to you from Calc 2, two polynomials are going to have the same derivative precisely if they differ by a constant. So that's really what we're saying here. Two polynomials are equivalent if and only if they differ by a constant. So show that this is an equivalence relation. So I'll go through that quickly. For reflexive, you want to know, is f equivalent to f? Well, the derivative of f is certainly equal to the derivative of f for all f. So that's no problem. Symmetry. If f is related to g, is g related to f? So this means the derivative of f equals the derivative of g is the derivative of g equal to the derivative of f. Well, if f and g have the same derivative, then certainly g and f have the same derivative, so it's certainly symmetric. And in terms of transitive, if f is related to g and g is related to h, is f related to h? So in other words, we're given the derivative of f is the derivative of g, and the derivative of g is equal to the derivative of h. Is the derivative of f equal to the derivative of h? And it certainly is the case that if f prime and g prime are the same polynomial, and g prime and h prime are the same polynomial, then f prime and h prime are the same polynomial. So there's your transitivity. So this is pretty easily seen to be an equivalence relation. Now, what can we do with it? How many equivalence classes are there? Well, again, if you think about it, polynomials are considered to be equivalent if they have the same derivative. Well, let's just start listing various polynomials. Simple polynomials. 1x, x squared, x cubed, x to the fourth, x to the fifth. These all have different derivatives. So all of these live in different classes. So there are an infinite number of classes. Because again, the derivative of this is 0, the derivative of this is 1, the derivative of this is 2x, the derivative of this is 3x squared, the derivative of this is 4x cubed. They all have different derivatives, so they all live in different classes. Next, how many elements are in each class? Well, again, if you think about it, if you took f of x and you took f of x plus 1, these have the same derivative. They live in the same class, but they're different polynomials. What about f of x plus 2? Same derivative as these, so they live in the same class, but it's a different polynomial. In fact, if you take f of x plus any real number c, this lives in the same class as f of x. But again, there are an infinite number of choices for c. So for any polynomial, by adding on a constant, you get an infinite number of other polynomials in that class. So not only are there an infinite number of classes, but there are an infinite number of elements in each class. Moving to D, list 5 elements in the equivalence class of X. Well, what we can see is if you have a class, if you just start adding constants, you get new elements of the class. So if you want 5 elements in the equivalence class of X, just keep adding on constants. Similarly, let's move this over here. If we want 5 things in the class of 6x squared minus 2x plus 8, all you have to do to get new elements in the class are just add or subtract numbers. So we want 6x squared minus 2x is in this class. 6x squared minus 2x plus 1 is in this class. 6x squared minus 2x minus 1 is in this class. 6x squared minus 2x plus 2 is in this class. 6x squared minus 2x minus 2 is in this class. In other words, anything in the form 6x squared minus 2x plus a constant lives in this class. So there are 5 elements in the set. Again, just take this, and if you add or subtract any number, you get a new element of the class. So that takes care of number 29. Let's move on to 31. That'll get us to page 9. And I think I said 31. Okay, 31. Let's see. Q is a set of polynomials with rational coefficients, and then define tilde as f is equivalent to g if and only if f of 1 equals g of 1 and f of minus 1 equals g of minus 1. So this requires a little bit of thought. So f is equivalent to g if and only if f of 1 equals g of 1 and f of negative 1 equals g of negative 1. Well, before we jump right into this, let's sort of play. This means if you take the polynomial f minus g and plug in 1, you get 0. If you take the polynomial f minus g and plug in negative 1, you get 0. That means the polynomial f minus g has both 1 and negative 1 as a root. That means f minus g is a polynomial times, well, what's the simplest thing that has both 1 and negative 1 as a root? X squared minus 1. So this means f minus g has to be some polynomial times x squared minus 1, or if you've got some polynomial g, then everything that is equivalent to it looks like g plus a polynomial times x squared minus 1. Now, let's dig in. Show that this is an equivalence relation. Well, I'll talk my way through it. Is f related to f? Well, f of 1 and f of 1 are the same. F of minus 1 and g of minus 1 are the same. Reflexive. What about symmetric? If f is related to g, then f and g give you the same value at 1, and f and g give you the same value at minus 1. If you want to know if g is related to f, then you're saying, does g give you the same value as f at 1? Well, yes, if f of 1 equals g of 1, then g of 1 equals f of 1. And similarly, does g give you the same value as f at negative 1? Well, if f of negative 1 equals g of negative 1, then g of negative 1 equals f of negative 1. So it's also symmetric. And again, similarly for transitive, if f is related to g and g is related to h, then f and g give you the same value at 1. G and h give you the same value at 1. So f and h have to give you the same value at 1. And the same thing is true for negative 1. So this is an equivalence relation. I went through that quickly, but I think you're pretty experienced at these things. Now let's move on to the harder parts of the problem. How many equivalence classes are there? Well, if we think about it, you could look at this more abstract or full answer, that f is related to g if and only if one of them is the other one plus a multiple of x squared minus 1. Or you could just, look at the following. Look at the polynomial 1. Look at the constants. Constant polynomial 1, constant polynomial 2, constant polynomial 3, constant polynomial 4, constant polynomial 5, constant polynomial 6. Look at all these constant polynomials. These polynomials disagree at 1, so they're not related. These polynomials also disagree at -1, so again, they're not related. So the point is, all of these constant polynomials live in different equivalence classes. So the answer to part B is, how many equivalence classes are there? An infinite number. Let's move to C. For C, how many elements are in each equivalence class? Well, again, if you take the equivalence class of G, then G is in the class, but so is G plus any multiple of x squared minus 1. In other words, when you plug 1 into this, you get G of 1. When you plug -1 into this, you get G of 1. This is in the same class as G of x. But so is this. In other words, as long as this piece vanishes when you plug in -1, this polynomial agrees with G when you plug in 1 and -1. So all of these polynomials live in the same class as G, but they're different. And all I've been putting here are constants. I could put more complicated things here than constants and get yet new elements of the equivalence class of G. So the equivalence class of G contains all of these things, or the equivalence class of G contains this for every different polynomial P. So you can get polynomials of all different types of degrees living in this equivalence class. So the answer to C, how many elements are in each equivalence class? Again, infinite number. Moving on to D. Moving on to D, list 5 elements in the equivalence class of 1. Well, as we can see from here, once you have something in a class, and you start on adding copies of x squared minus 1, I mean, this is an easy way to do it, but there are other ways to do this. Notice all of these live in the equivalence class of 1, because as long as you just add on a multiple of x squared minus 1, you're staying in the class. And moving to E, list 5 elements of the equivalence class of x. Well, same reasoning. If you start with x, and you start on adding copies of x squared minus 1, like so. And again, I don't have to just be putting constants here. I could be putting any polynomial here. But if you start with x and you start on tacking on multiples of x squared minus 1, you get additional things in the equivalence class of x. So the equivalence class of x contains, as they all do, an infinite number of different polynomials. That takes care of 31. Let's move to 32. This will be page 10. (4.3), that was number 32 we're coming up to. Okay, 4.3, number 32. Now we're going to look at polynomials that are considered to be equivalent These are polynomials with rational coefficients. If and only if they agree at the square root of 2. Well, let's use some of our familiar ideas here. This is the same as saying, if you take the polynomial f minus g and you plug in the square root of 2, you get 0. That means f minus g has the square root of 2 as a root. But as we talked about in class, any polynomial with rational coefficients, because again, we're looking at things with rational coefficients, any polynomial with rational coefficients that has the square root of 2 as a root is a multiple of x squared minus 2. So f of x minus g of x is some polynomial times x squared minus 2. So if you've got some polynomial g, then everything in its equivalence class just looks like that polynomial plus a multiple of x squared minus 2. Well, if you think about showing that this is an equivalence relation, this is really the same problem as 31. The problem for 31 was we had an x squared minus 1 here. Now we have an x squared minus 2 here. But again, same exact argument as in the previous problem would show that this is an equivalence relation. So let's move to the other parts of the problem. How many equivalence classes are there? Well, just like before, all of these constant polynomials live in different equivalence classes because they all give you different values of the square root of 2. So, infinite number of classes. Next, how many elements in each equivalence class? Well, again, we could see if you started with some polynomial g, if you just keep adding on multiples of x squared minus 2, so notice each of these are all in the same equivalence class, but they're all different. So again, each equivalence class has an infinite number of elements. Again, this is just like the previous problem. List 5 elements in the equivalence class of 2. Well, again, just start adding on copies of x squared minus 2. And these are all in the same equivalence class. And then for E, just like before, if you want elements in the equivalence class of x, you just keep on adding copies of x squared minus 2. And again, just as we said for the previous problem, I'm adding on constant multiples of x squared minus 2. I could be adding on any multiple of x squared minus 2. So I've only listed out 4, but you can see how you could certainly get an infinite number of different elements here. And that takes care of number 32. Let's move on to number 33. This will be page 11. Number 33. In this case, we look at the set of ordered pairs where A and B are integers, and B is not 0. So this sort of is the same set we used to start defining the rational numbers, but the difference is now we say that AB is equivalent to CD if and only if A times B equals C times D, which is a different equivalence class than when we define the rational numbers. We want to prove that multiplication is well defined. And here's how we define multiplication. The class containing AB times the class containing CD is the class containing AC, comma, BD. So now, to prove it's well defined, we have to show that if we change the name of this class and we change the name of this class, we get the same answer. So we're given two names for the first class. And we're given two names for the second class. We have to show that if you take the product using the first set of names, it's the same as the product using the second set of names. So if you change the name of the first class, keeping it, of course, the same class, and you change the name of the second class, again, keeping it the same class, you want to show that we get the same answer. So here's what we know. Since these are the same, A1, B1 equals A2, B2. And we know C1, D1 equals C2, D2. We have to show, well, let's think about the way the multiplication is defined here. This product is set to be A1, C1, B1, D1. This product is A2, C2, B2, D2. And we have to show that these two classes are the same. Well, what's the test for whether these two classes are the same? If this product equals this product. So we have to show A1, C1, B1, D1 is equal to A2, C2, B2, D2. Well, let's play. Okay, we'll start with A1, C1, B1, D1. And we want to turn it into this. But from what we know, we can replace the A1, B1 by A2, B2. So this becomes A2, B2, C1, D1. But this one tells us that we can replace C1, D1 by C2, D2. And the commutative and associative laws say that we can switch these. We get A2, C2, B2, D2. So if this is true, meaning we have two names for the first class, and if this is true, meaning we have two names for the second class, then if we multiply them using the first set of names and we multiply them using the second set of names, we get things which are equivalent, meaning multiplication is indeed well defined. That takes care of 33. Let's move to 37B, which would be page 12 now for us. Okay, 37B. We're going to say that two polynomials with rational coefficients are equivalent if and only if their difference is a constant. And we define addition and multiplication by adding their names. We want an example that shows that multiplication is not well defined. So again, here's how we define multiplication. The class containing F times the class containing G is the class containing F times G. And we want to show that multiplication is not well defined. Namely, if we change the name of the classes, or at least one out of two classes, that we can get a different answer when we multiply. So let's just play. Let's take two names for class number 1. Again, these are the same because x and x plus 1 differ by a constant. Let's take x and x. In other words, you don't have to choose a completely different name. Now, when we multiply, according to this, we get the equivalence class of x times x, or x squared. According to this, we get the equivalence class of x plus 1 times x, or x squared plus x. In other words, we changed the name of class number 1. We kept the name of class number 2 the same, but when we multiply just by merely changing the name of class number 1, we got a different answer. So just by changing the name of a class, because again, notice these two polynomials differ by x, they don't differ by a constant, so multiplication not well defined. So that's 37b. Next up is 41. Again, page 13 of our notes. So in 41, we're going to say that two integers are equivalent if and only if their difference is divisible by 10. It's an equivalence relation. We define addition by adding the names. We define multiplication by finding the names. We want to find a positive integer so we want a positive integer s such that s plus 7 is equal to 0, where the class of s plus the class of 7 is equal to 0. Well, there are various ways that you can try this. One is trial and error. And when you do trial and error, the first thing that's going to work is 3. Because the class of 3 plus the class of 7 is the class of 10, which is the same as the class of 0. So one is you can just try trial and error. If you plug in 1, you get the class of 8. If you plug in 2, you get the class of 9. If you plug in 3, you get the class of 10, but that's the same as the class of 0. Another way to look at it is s equals minus 7, or the class minus 7, also it works here because the class of minus 7 plus the class of 7 is equal to 0, but that's not a positive number. The way you get new elements in a class is to add or subtract copies of 10. If I subtract copies of 10, I'm going to be more negative. If I add copies of 10, the first copy of 10 that I can add and get a positive number is to add 10 once and get 3. Now, there are lots of other answers that will work. 3 is the smallest positive integer that will work, but so will 13, 23, 33, 43, etc. Next, we want a positive integer t such that the class of t plus the class of 4 is equal to the class of 2. Well, two ways to go about this. One, you can sort of do trial and error and keep on going until, t equals 1, t equals 2, t equals 3, t equals 4. Finally, when you get t equals 8, this is the class of 12, and the class of 12 and the class of 2 are the same. So one way is, again, just trial and error, counting t equals 1, 2, 3, and the first one that works is 8. Or you can look at this and say, well, if these were ordinary numbers, then if t plus 4 is 2, then minus 2 would work. So the class of minus 2 will do the trick. But if the class of minus 2 does the trick, then all I need to do is find positive numbers in the class of negative 2. I can find positive numbers in a class of -2 simply by adding on copies of 10. Well, adding on one copy of 10 to -2 gets me 8. So there's my 8. Moving on to C, find a positive integer such the class of u times the class of 7 is equal to the class of 1. For something like this, I would suggest happily using trial and error. If u is equal to 1, you get the class of 7 here. That's not the class of 1. U is equal to 2 gives you the class of 14, which is the class of 4. That's not 1. If u is equal to 3, you get the class of 21 here, but the class of 21 is the same as the class of 1. So u equals 3 does the trick. Again, if you've got a calculator, trial and error, not a hard thing to do. Next, find a positive integer v such that, so positive integer, such that the class of v times the class of 7 is equal to the class of 9. Well, again, trial and error. If v is equal to 1, this is a 7. If v is equal to 2, this is 14, which is a class of 4. If v is equal to 3, this is 21, which is the class of 1. If v is equal to 4, this is the class of 28, which is the class of 8. If v is equal to 5, this is the class of 35, which is the class of 5. If v is equal to 6, this is the class of 42, which is the class of 2. If v is equal to 7, this is the class of 49, which is a 9. Bingo! V equals 7 does the trick, as well as 17, 27, 37, and so on. And finally, for the last part of this problem, for part E, find a positive integer such that, so positive integer such that the class of W times the class of 8 is equal to the class of 0. And again, nothing in the world wrong with trial and error. If W is 1, you get the class of 8. If W is 2, you get the class of 16, which is the class of 6. If W is 3, you get the class of 24, which is the class of 4. If W is 4, you get the class of 32, which is the class of 2. And if W is 5, you get the class of 40, which is the same as the class of 0. So W equals 5 will do the trick. And I believe the final problem from the session is 43B. So this will be page 14. (43B) says we're going to look at real numbers, and we're going to say that they're equivalent if the difference is an integer. And for 43B, someone wants an example that illustrates that multiplication is not well defined. Well, let's just simply play. So we're dealing with real numbers, and we're going to say that they're equivalent if their difference is an integer. And we want to show that multiplication is not well defined. So let's just play. Okay. Well, let me take some things that aren't integers. Like the class of 1/2 is the same as the class of 3/2 because their difference is 1 or -1, depending upon how you look at it. Let's see, the class of 2/3 is the same as the class of 5/3. because they differ by 1. Well, let's see what happens when we multiply. According to this, when you multiply, you get 1/2 times 2/3. This is a class of 1/3. When you multiply these, and you multiply, it looks like you get the class of 5/2. So let's double check. 1/2 is in the same class as 3/2 because the difference is 1 or minus 1 depending upon how you look at it. So these are two names for the same class. The class of 2/3 and the class of 5/3 are the same because their difference is 1 or minus 1 depending upon how you look at it. If we multiply, this becomes the class of 1/3. This becomes the class of 5/2. 1/3 and 5/2 do not differ by an integer. So in other words, we changed the names of the classes and we got different answers. So multiplication not well defined. Well, I hope you found this useful. I sure hope I am successful with the technology that you'll have both audio and visual, and I can put this on the internet. Again, in addition to putting this on the internet, I will also take the whatever 15 pages of notes and store them as a PDF file. But for now, any other questions, just send me an email, and I will hopefully be able to get this thing online in the next couple of hours. Have a great weekend.